Hello, everyone. So welcome to my talk. I know it's pretty late, so I will make this talk interesting for sure. Yeah. OK, so here's the talk. So the CableMon, improving the reliability of the cable broadband networks with the proactive network maintenance. And I will introduce this work with the cooperation with the CableLabs and also UNC. So firstly, cable broadband networks play an important role in the modern life. It enables the e-commerce, and also it offers the opportunity for remote study, work, and entertainment. Cable networks are one of the few choices in the US. A recent study shows that around 93% of US homes has the availability to cable networks, which is much higher than the other two alternatives. So, however, cable networks are unreliable. So, as shown in the figure, the partly reason is that this HFC or hybrid fiber coaxial architecture. So, this HFC architecture contains not only the fiber optics, but also the coaxial cables. So, unlike these fiber optics, the coaxial cables are more vulnerable to the radio frequency interference. And also, many parts of the coaxial cables are already decades of old. And the aging of the problem can lead to the problems such as the cable shielding erosion, the loose connectors, the broken amplifiers, and so on. And a recent study shows that the reliability of the broadband network is at most 2 nines, which is only 99%. It is much lower than the FCC's requirement for the public switched telephone network, which is 4 nines here. So given this observation, here comes our ultimate goal, is to improve the reliability of the cable broadband networks. So this slide shows the roadmap of this talk. Firstly, I will introduce the limitation of the existing work. Then I will introduce our system CableMon. I will start with the high-level ideas, and following by the challenges we face during designing CableMon. And also, I will propose the solutions to these challenges, and I will suggest the ways that ISP can deploy our system. Also, I will have the evaluation results for our system and also our conclusion. OK. So now I will start with the limitation of the existing work. So of course, the broadband network is not something new. So that the cable industry has already recognized this problem, the unreliable problem. Therefore, they have already developed a framework called proactive network maintenance, or PNM here. So in this figure, we can see 2 network devices, which is the cable modem, or CM, and the cable modem termination systems, or CMTS. The CMTS will communicate with the CMs periodically with the DOCSIS, which is a standard defined by CableLabs. Also, we have another monitoring server to collect this data from the CMTS with the SNMP protocol. And we call this part of data as the PM data here. For example, it can collect the signal-to-noise ratio, or SNR value, for the CMs from the CMTS. The existing work that the ISPs currently use the manually set threshold here. So that means if a metric is below or above a certain threshold, then the network needs to be repaired. However, we found that it is pretty hard to determine this proper threshold manually, because if we define this threshold too aggressively, then the ISP will suffer from the high false positives. Otherwise, on the other hand, if this threshold is too conservatively, then the ISP could lose many opportunities to fix problems. And we found that for the current recommendations, the ISPs still suffer from the high false positives. For example, in one of our studies, we found that even over 25% of modems need repair if we follow the suggestions provided by the PMM best practice document, which is the instruction to use the PM data now. Okay, in order to resolve this problem, we designed a system called CableMon. The high-level idea of the system design is that we want to use the customer trouble tickets as the hints to learn what pattern of the PM data may indicate a network fault. So before going into detail for this high-level idea, I will introduce several design goals here. So the high-level goal of our system is basically to save the operational costs for the ISP by forecasting the troubles before customer calls in. We learned from our collaboration ISP that even if a 10% of reduction of these customer tickets can save their operational costs significantly. Also, we want to avoid the manual labeling. So one way to think of this anomaly detection work is that we can input the data and the label into a supervised learning model to train a model and to predict the results. Unfortunately, we do not have the ground truth or label here because think of this way. If the ISP already knows exactly when the anomaly begins and ends, then they already finished this work, right? So that's, and also our data set is very huge, and it is not doable in practice to label data manually. So that's why also the intuition behind the customer trouble tickets we use here. Thirdly, because we want to provide a tool to the ISP to detect the failures, therefore, there shouldn't be any extensive parameter tuning on the ISP side. Finally, so we want the tool, the detection, to be online so that the system should be efficient enough to do this. Okay, so now I will show how our data set looks like in this slide. We mainly have two parts of data set, as I mentioned just now. One is the PM data, and another is the customer trouble tickets. The PM data is collected from the cable modems. And from this figure, we can show that each cable modem has a bunch of PM data points along the timeline. We collected these data points periodically with roughly 4 hours. And each data point could contain a list of PM metrics, such as the transmission power, the receiving power, and so on. And meanwhile, a customer ticket can be reported to a certain modem at a certain timestamp. And similarly, in our data set, this custom ticket also contains a list of ticket fields, such as the account number that reports these tickets, the description for these tickets, the action, and so on. The full list of the PM metrics and also the ticket fields can be found in paper. We describe it in very detailed things. So here comes a very important observation that the tickets has a strong correlation with the network faults. So firstly, we define the average number of tickets per unit as the ticketing rate. So it's basically the number of tickets divided by the length of time period for these tickets to be reported. So from this figure, we can see that when the SNR decreases, becomes too low, the ticketing rate increases and becomes higher. Here, normalize means that we normalize this ticketing rate with the baseline ticketing rate, which is simply the total number of tickets divided by the total time. And this indicates that this ticketing rate, all the tickets, is correlated with network faults and offers our insights of this work naturally that we treat the tickets as the hints to detect the network faults, even if we do not have any ground truth. So here comes the challenge to use this. So firstly, the tickets are noisy. So ideally, if every customer only report tickets when something happens, some network relevant issues happen, then we can simply treat this ticket as a ground truth and still input it into the supervised learning tools. However, this is not true for sure, because customers may call for the network irrelevant issues. And vice versa, they may keep silent when something indeed happens. Furthermore, the PM data is also noisy, and the PM data contains the instantaneous channel conditions, which is not sufficient for fault detection because it does not reflect the trend of the data. And as I said, the data, PM data also include the noise, which makes it harder to train the model. So to overcome the first challenge, we filter out the non-ticket related tickets with the ticket fields, such as the description, action, and dispatched. For example, if we see a ticket with the action as the customer education, that means the ISP simply resolves the tickets by educating the customer over phone. So it is very unlikely to be a network relevant ticket. And from this figure, we can show that after the ticket is filtered, this filtered tickets has an even stronger correlation with the network faults. And that's why we use these filtered tickets as the stronger ground truth in our model. And next, for the challenge of the PM data, we apply the statistical models to firstly smooth the data to get rid of the noises. And secondly, we want to generate more features from the PM matrix. So here, I will list several statistical models we used. For example, the moving average, and the weighted moving average, and also weighted moving average difference. And finally, variance. We have a lot more besides these 4, and this can also be found in the paper. OK, so now we get a larger set of features for the detection. And here, I will show how we determine the threshold without any manual efforts. So in this figure, we can find that we have a bunch of data points with 3 tickets comes along the timeline. And if we randomly choose a threshold as threshold 1 here, then the 3 points below this threshold is regarded as abnormal, which I labeled as the red points here. And the rest of the green points are the normal points. Then we can label the timeline with its nearest data point. For example, in this case, we have 3 abnormal periods around these 3 abnormal points, and all other parts are regarded as normal periods. And we can calculate the ticketing rate for the normal periods. So for example, in this case, we have 1 ticket fall into the normal periods and 10 data points. Remind that we collected the data points roughly 4 hours. So that 10 data points means 40 hours. Then the normal ticketing rate in this example is 1/40. And similarly, we can also get the abnormal ticketing rate as 2/12. Then we can define the ticketing rate ratio as the abnormal ticketing rate divided by the normal ticketing rate, which is 6.67 in this example. If we raise the threshold from threshold 1 to threshold 2, then we have more abnormal points and therefore more abnormal periods. And of course, we can still calculate the normal ticketing rate as 1/20 and abnormal ticketing rate as 2/32 in this example. And also the ticketing rate ratio, which is 1.25 for threshold 2, which is much lower than the one for threshold 1. So the main idea here is that we want to iterate all possible thresholds and choose the threshold that could maximize the ticketing rate ratio here. So intuitively, we put as many tickets as possible in a short period by selecting this threshold. To provide more intuition under this approach, I provide 2 properties to the ticketing rate ratio. So firstly, it is monotonously decreasing with respect to both false positives and false negatives. And secondly, it is maximized if and only if both the false positives and false negatives are 0. And we have a formal proof in the paper besides this intuition. So given this threshold selecting algorithm, then we can select in the top features by simply select the features that can achieve the highest ticketing rate ratio. And remind that we generate the features from the PM matrix with the statistical models. And when we build a model for the features generated from the same metric, we will select at most 2 of them. So this table shows the top 5 features we selected in our experiment. For example, the top 1 is the SNR variance, which achieves the ticketing rate ratio as high as over 14. Then after selecting these features, we combine the features by simply, if one feature is abnormal, then we regard the whole data points as abnormal. This is based on the observation that different features may detect different type of network faults. And because we already select the threshold to maximize the ticketing rate ratio for each feature, we expect that by combining them, we can still get a high ticketing rate ratio. And ISPs can use CableMon in two ways. So firstly, they can do the proactive detection. That means they can make a dispatch decision only after a fault persists. We have a sliding window algorithm to convert the point-wise detection I introduced just now to an abnormal event detection algorithm. So because of limit of time, I will leave details in the paper. And secondly, the ISP can do the diagnosis work. That means it can determine whether, when the customer calls in, whether the customer reported the ticket, the problem is indeed network relevant. OK, now we come into the evaluation results. We use the datasets from January to August in 2019. So we use the data from January to June for training and the rest of them for testing. We compare our system with other approaches, including the cutting-edge ISP tools, which use a manually set threshold, and SVM, and decision tree, and random forest. So ideally, we want to deploy our system in a real-world deployment and to see how many tickets it can reduce it for ISP. However, this work is still in the progress. So that in our experiment, we emulate how ISPs use CableMon with the sliding window algorithm, and we count the number of tickets arrived during an abnormal event. So we have three metrics. Firstly is the ticket prediction accuracy, which is the number of predicted anomalies that can be associated with at least one customer ticket, divided by total number of detected anomalies. And also similarly, for the ticket coverage, it's simply the number of detected tickets divided by the total number of tickets. And we also measure the normalized ticketing rate for each tour. This table shows the results of these three metrics, and we can find that the CableMon did pretty well for all the three metrics. We also examined the ticketing coverage because the number is not high enough, and we found that even if after filtering the tickets, there are still many PM irrelevant tickets, and we also confirmed these results with the ISP's expert. So note that the ISP tool achieves a slightly higher ticketing coverage here. However, it is with the cost of a pretty low ticket prediction accuracy and a normalized ticketing rate. And we also provide some ticketing statistics here. So this figure shows the ticketing lifetime, which is the time from ticketing opening to closing. And we can find that the tickets detected by CableMon last for longer time, and it may indicate harder issues. And similarly, for this figure, we can see that the type of tickets indicates that these tickets are more severe and need more dispatches. And we have more interesting results in the paper. And finally, here's our conclusion. So firstly, we built CableMon to detect network faults. And we use the tickets as a hint to avoid the manual labeling and to overcome the no ground truth challenge. And we overcome the noise from both the PM data and the customer trouble tickets. And finally, we found our experiment shows that CableMon can achieve high ticket prediction accuracy and moderate ticket coverage. OK, thanks. Any questions?
I'm Max from Google. Thank you for the talk. It's pretty interesting.
Okay, thank you.
So I'm curious, based on the data you get and the decision you make, will you also be able to identify what is wrong instead of just saying there's something wrong with the network? Or is that a useful thing to ask?
Yeah, you get it. That's our future work. Okay. So currently, we only do the binary detection. That means we either abnormal or normal. Right. But we are thinking of ways to do some more maybe final detection to classify the anomalies. For example, because we have multiple features, and we can select the 1 or 0 means abnormal or normal for each feature, and get this as a vector. Mm-hmm. And this is still in progress. Yeah, you get it.
Cool.
Yeah, thank you.
Arpit Gupta from UCSB. Mm-hmm. So I have a question. So the data is collected every 4 hours.
Yes.
Is there any reason why it's collected at this frequency?
That is defined in the PM framework, or basically the PM best practice document. So there are 3 intervals, if I remember correctly, which is 10 minutes, 4 hours, and 12 hours. However, the ISP argue that 10 minutes might be too expensive to measure, so that's why we selected another standard as 4 hours.
So 4 hours, like...
I'm sorry, we'll have to cut that off right now. You have to take it offline. So let's thank the speaker again.